Hey guys, Mr. L coming back at you with another video. And in this video, we're gonna go in a little bit more depth about entropy. We're gonna talk about the Boltzmann distribution of particles and statistical thermodynamics. We're gonna see how entropy changes with phase, in which phase has more or less entropy, and how to calculate the change in entropy looking up published values. So let's get into this video. So the first thing we're going to talk about is entropy at the molecular level, or the idea of statistical thermodynamics. This was first thought about by a guy named Boltzmann. And if we have this thought experiment here where we've got two particles on one side of a flask, a red one or a green one or whatever, you've got two different particles, and then you've got some empty flask on the other side. So if we open the flask, there's four possible outcomes that can occur here. You could have one particle going to the other side. You could have the other particle going to the other side, neither particle moves, or both particles move. So we've got a 1 out of 2 chance existing for whatever flask you want to calculate for, and you got two possible outcomes. So you would have 1/2 squared. If we're thinking about bulk properties though, if we're thinking about millions and millions of particles, like an Avogadro's number of particles, and we were to take that 1 out of 2 chance and raise that to Avogadro's number of particles, we could see that statistically this is not going to happen to where all the particles just go on the other side. And we could see that in bulk matter, that if we have some gas in some flask and we open a vacuum flask to the other side, you're going to have an equal distribution, or about 50-50 mix of the gas once it can spread out to the other container. So this is how we have to start thinking about things. We actually have individual particles, but what do we actually observe on the full scale? So in order to understand things at the molecular level and translate that to bulk properties or at the macro scale, what we're going to need to do is we're going to need to think about this Boltzmann equation that we have here, where entropy, S, is equal to Boltzmann constant K times the natural log of W, which is a microstate. So let's talk about microstates a little bit. So the symbol W is going to be considered a possible arrangement. So we've got some compound here, and this compound can move in all different directions, all different ways. You've got translational motion. Translational motion means the particle itself is just going to move around the container and bounce around. The next one we have is vibrational modes. So vibrational modes could happen where we've got some bending and oscillating of the particle within its own bonds. So as long as there's heat, there's going to be some oscillation due to those electron clouds randomly moving around. You might have fluctuations in the pi bonds getting squeezed together, or you might have some actual elongation of these bonds. So when we do infrared spectroscopy, that's what we're doing. We're exciting these bonds by putting in infrared radiation, and they vibrate in different vibrational modes. So that's vibrational energy. And then the last one that we have is rotational energy. So these things can rotate in space, as well as they can rotate around a bond axis. So along this bond, we can have some rotational energy going on here. So hopefully you have a little bit better understanding of what a microstate is and how these things can move around. So let's go back to the Boltzmann equation and try to see what this actually means. So if we want to find the change in entropy, we're going to need to find the change in microstates. So we'd have to take the same thing, the whole equation final minus the whole equation initial, where you've got some final microstates and initial microstates. And if we're working with logarithms and you're subtracting two different logarithms, that's the same thing as dividing of whatever's inside that natural log term. So we're going to have microstates final over microstates initial. Boltzmann constant's just a constant, so for our idea to grasp this equation, we really just need to focus on the change in microstates. So let's think about a fraction. We've got some numbers on top and the bottom of the fraction, and we're going to take the natural log of that. Well, if you've got a calculator and we've got more microstates final than we began with, we're going to have a number greater than 1. Anything greater than 1, you take the natural log of it and you get a positive value. So that means if you have more possible microstates available at the end than you did at the beginning, you've increased the amount of randomness in your system. Now let's think about, we can't have negative microstates, but we can have this fraction be below 1. If we've got the denominator bigger than the numerator, so maybe we got 1 on top and 50 on the bottom of this fraction, and we plug a decimal value into a natural log, we get a negative value output. So that means that we would have more possible microstates that we began with than what we ended with. Therefore, you ordered the system. You organized the system. So the numerical value of randomness that you get is going to be a decrease in the number of randomness value. So you're going to have a negative number. So there's some things that can alter our randomness or our entropy value. If you increase the volume of a system, your randomness is going to go up because now you've got twice the amount of space. Say you doubled the space, now you've got twice the amount of space for those particles to exist and move around in, bounce around and vibrate in. So you've got all these different possible orientations if you increase the volume. The other thing that you could do is increase the temperature, and since all of these things are oscillating and vibrating, when they got more heat, they're just going to oscillate and vibrate even more rapidly with more energy. So this is going to increase the amount of randomness that you have. And the last thing is if you've got more particles, say you have 1 mole of particles versus 2 moles of particles, you're going to have way more randomness with more particles because now you have more possible orientations that could occur within the container. So now let's talk about different entropy values in regards to phase change or different phases. We've got the solid phase. That's going to be the most organized, least entropic value. It's going to be the lowest entropy value. So solid is typically organized in a very rigid structure, a crystalline structure. Then you start to heat this object and those bonds are going to start to break, and now the particles are able to flow past each other in the liquid phase. So you're increasing the randomness by changing phase to liquid, but they're still fairly clumped together. You keep heating it and now particles are able to overcome those intermolecular forces and fly off into different parts of the container. Now you're in the gas phase and these particles are much greatly separated, so there's way more entropy, the higher entropy value. Then you've got the special case of aqueous where you got to be careful. So if we're talking about something like salt, sodium chloride, and we dissolve that in water, the crystals are breaking apart into individual ions that are getting solvated. So the ions are not going to be in this crystal structure, so they're going to be spread around that container that you've got your aqueous solutions in, and it's going to become more random in regards to the salt. If you're talking about the solvent though, the solvent has to organize itself around each ion in order for that thing to dissolve. So you're organizing the solvent. So you're going to have a decrease in randomness in regards to the solvent. So that brings us to our third law of thermodynamics. The third law of thermodynamics, we're going to go back to the Boltzmann equation, and we can see that again, delta S is equal to Boltzmann constant times natural log of microstates final over microstates initial. So let's say we have no change in microstates. So that means you're going to have a value of the same number on top and the bottom of the fraction, which is a 1. And if we take the natural log of 1, the value is 0. So that means we've got 0 change in entropy. There's been no change in microstates. Everything is a perfect crystal lattice. So therefore, at absolute 0, we have 0 randomness. So if we've got some substance and absolute 0, we've got 0 randomness, we're going to start to put in heat, and that solid is going to begin, the particles are going to begin to vibrate. It's going to become more and more violent and moving around a lot more. Then you're going to hit the phase change, the melting point. The temperature of the object is no longer going to continue to rise. You're going to hit a barrier at the melting point, and all of the heat is going to be used to convert that solid into liquid, so you're going to have that entire melting action. Then once you've fully melted that thing, whatever substance it is, then the temperature of that substance can begin to creep up until you hit the boiling point. Then the temperature is going to remain the same. All the heat is going to be causing boiling to occur, increasing the randomness, and then you're eventually going to have the gas phase of that substance. So when you're looking at these kinds of chart, realize that at absolute 0, there's no molecular motion, and then at each of the phase changes, you go vertical because you've got no temperature change and all the heat is being used to increase the amount of randomness. So the last thing we're going to talk about today is how do we calculate the change in randomness, delta S of a reaction, when we've got these different published values. And like I showed you in a previous video, we typically pull published values out of books. Textbooks, they're usually going to be in the back, or you're going to have this chemistry physics handbook in your lab. So we're going to have to look up these values, and these are standardized values at 25 degrees Celsius, 298 Kelvin at 1 atmosphere of pressure. So you're going to have some reaction, and you're going to have molar values because you balanced your reaction. And so just like delta H calculation, you're going to do final minus initial or products minus reactants. So you're going to take the sum of all the molar values of the products, and you're just going to look them up, and they're in units joule per mole Kelvin. And you're going to subtract the molar value times the reactant value. So you're always going to have a value. It's not like delta H where you've got the allotropic form, the enthalpy of formation 0. No, the only time delta S is ever going to be 0 is at absolute 0. And since we're doing this at 298 Kelvin, that's not absolute 0. So every value you pull from your handbook better be a value that's not 0. They all have a randomness value. So some other things that we can think about when we're thinking about the change in randomness is randomness is going to be higher with higher number of molar mass. So if we have something like a molar mass of 25 versus 45, the one that has higher molar mass is going to have more electrons in their cloud region. They're going to vibrate more randomly in different orientations. So the randomness value is going to be higher with higher molar mass. The other thing to think about is if you've got two particles that might have the same molar mass, but you've got one that's split into two pieces, the two pieces are able to move around the room more independent from each other versus the thing that has the same mass but clumped together. So if you've got more number of particles, you're going to have higher randomness value. So there it is, you guys. There's the video on Boltzmann statistical thermodynamics and how that relates to randomness, how we can calculate the change in randomness looking up published values, and how randomness varies with different phases. So if you like this video, send it to your favorite lichen, send it to your favorite automobile manufacturer, and we'll see you in the next video.